Alright, so now we're going to learn how to identify feedback by the type, by its type. And we have two different types of feedback that we can use. One is series feedback, and in series feedback, at an amplifier's ports, the signal must go through both the feedback network and the amplifier to get to ground. So we'll just say that the signal must traverse both the amplifier and the feedback network. So we'll draw this series type feedback, for instance, at the input. So here we would put our input into the amplifier. We would have to go through the amplifier's port into the feedback network and ultimately return through the feedback network back to either the input source, or we commonly ground one side of the input source. So this is our input signal, V sub I. Our feedback signal would come across the output of the feedback network, V beta. And our error signal, V sub E, would go across the input of the amplifier. Now, if our feedback is shunt, our feedback is connected in parallel at the amplifier ports and the feedback port. So what we say is our signal can traverse either the amplifier or the feedback network to get to ground. So in this case, you can imagine our amplifier here is feeding our signal to an output, V sub O, and we would connect that output and amplifier in parallel with the feedback network that consists of beta. Now, we normally label our amplifiers by the types of feedback at the input and the output. So for instance, we put series feedback at the input and shunt feedback at the output. So this amplifier would be called a series shunt feedback amplifier. Now, knowing what we know about series connections and shunt connections, the series connection should increase the impedance at the input, which would mean that we would like to take a voltage input with this series shunt connection. And at the output, the shunt connection should reduce the impedance at the output, which also likely would mean that we would like to take a voltage output. Remember, a voltage amplifier, we want a small output resistance and a large input resistance. And our series shunt feedback creates a large impedance at the input and a small impedance at the output, ideal for a voltage amplifier. Let's look at a transistor level example. So imagine that we have this particular transistor amplifier consisting of a couple of common source stages that are cascaded together. And now note, we haven't shown any of the bias circuitry or loads for this particular example. We're assuming that the transistors are biased into the forward active region and that they are loaded appropriately. So let's say that we want to create a series shunt feedback. In other words, we want to make a voltage amplifier. Alright, so let's copy our transistor circuit here, and we're going to add some feedback to it. All right, to add that feedback, we're going to take some of the signal from the output and feed it back to the input. And we're going to do it with a voltage division. So I'm going to put a feedback resistor R sub F that feeds the signal back to the transistor at the input, and I'm going to do that through our voltage divider circuit. So here at the output we can see that our signal, our feedback is in shunt because I can go either through the feedback network to get to ground or the output through the transistor to get to ground. At the input, I've got my V beta signal, which is the voltage division ratio of these two resistors, and the signal from the positive side of the sorry, this is not feedback, this should be an error resistance, RE. The positive side of the error resistance is my error signal, V sub E. So basically what I see here is, to get to the output, I just have my output voltage going across the feedback network, but to get back to the input I have to go through my feedback circuit, my V beta, plus my error voltage. So the feedback voltage and the error voltage are in series. And this makes this a series shunt amplifier. Alright, so we'll stop there and look at a few more examples of feedback in a moment.